Alright, so today we're going to hopefully finish the topic of the logistic regression, okay? So this is the script that we did in the previous class. I'm going to run the script and you do the same thing, okay? Just select everything. I believe we finished right here. I have actually more than, hold on, let me erase that stuff, okay? Let me erase that. I believe this is where we finished, okay? So here's the summary. So we got our model, right? Logistic regression model, and in the logistic regression, we create a linear expression, just like this one, right? It's posted in the comments, okay? But instead of a numerical value, it predicts for us natural log of the odds that from that specific customer, the response is going to be 1, that they will accept an offer from the bank to get a loan, unsolicited, right? Okay, and I believe last thing that we kind of started to discuss was odds ratio, right? So let me kind of remind you. So let me go back to the OneNote. All right, so here's what we discussed in the previous class. We said that if I record, it actually should be here somewhere, right? Yeah. If I record my expression, okay, for the natural log of odds, that the response is going to be 1, then I'm going to look just at income right now, right? So this was my, let me erase some of that. This was my intercept. That was the slope times the income, and then I had plus dot dot dot. That means everything else, right? All the other variables, including do they have CD account, do they have securities account, do they do online banking, etc., etc. All the other things, right? And then we said, what will happen if income from the base level, current income, goes up by $1,000? Then on the right side, I'm going to have same intercept, same slope right here, okay? But now it's multiplied by income plus 1. And then I have plus dot dot dot. That's the rest of the variables, right? So if I take the line number 1 and subtract line number 2, what will happen is all the other variables will cancel out because they have identical values, right? Intercept will cancel out because it's the same everywhere, okay? Moreover, 0.0597 times income will cancel out on both sides, right? And I will have only 0.0597 times 1, okay? That's on the right side. And on the left side, I'm going to have natural log of odds at the, let's see, increased level of income minus the natural log of odds at the old level of income, right? And then somebody, I remember, Dylan, right? Dylan said that, well, if we have expression log minus log, and it's really log of the ratio, okay? So here it is. Natural log of odds at the level income plus 1 divided by odds at the old level is equal to the 0.0597. That's the slope. And then how do we get rid of the ln? We raise e to this power. E and ln are opposite functions, so essentially they cancel out. And on the left side we have odds ratio, okay, right here. We have odds ratio. And on the right hand side we have simply e to the power of the slope, okay? So it comes down to actually, let's see, interpretation of the slope, of the slope for the variable. For the logistic regression, the interpretation of the slope for each variable is different than from just regular linear regression, okay? There it is. This ratio right here on the left side is called unit odds ratio. Well, it's obvious why it's called odds ratio, right? It's odds 1 divided by odds 2. Why is it called unit? What do you think? Because it corresponds to, here, okay? Corresponds to variable plus 1 divided by variable before it was increased by 1, okay? So I add $1,000 to income, and that's basically the ratio that I calculate. What are the odds that the increased income plus $1,000 level compared to the old one before the raise? That's why it's called unit odds ratio, okay? All right, so now all I have to do really is compute that value, right? What's e to the power slope for the income. I actually can do that really quickly in the code. Okay, so go back to the code, and here's what I'm going to do. Let me put a comment. Okay, calculate exponent of the coefficient of the model. Okay, and that's literally what I'm going to do. So EXP, just like in Excel, EXP stands for exponent in R as well, okay? And what am I calculating? Exponent of what? Well, my model has coefficients, right? So here is my model summary, right there. Yes? This is my model summary, okay? So what I'm interested in really is compute the e to the power these coefficients right here, okay? Because 0.0597 is one of them, right? So it's very easy to do, actually. This is what I do. I call my model by name. What's it called? Multiple logistic regression model, right? That's the name of my model, right? And then I put the $sign, just like what I do when I try to access a column in the data set, right? Same thing here. Model, $sign, and it tells you what's inside the model. Do you see the coefficients? Yeah. So take model coefficients and raise e to the power pretty much all of them. Okay? That's probably something that you want to put on your study guides for upcoming exam. Yes? Yeah. So let's run this line. Okay? And all it does basically is it takes each and every slope and raises e to the power of that slope. So whatever we have listed in the model is going to calculate e to the power of that coefficient. Okay? All right, so which one I'm looking for? I'm looking for the one that relates to income, correct? This one. So 1.0615. Okay? Now let me go back to the OneNote. All right. So out of my calculations, here's what I found out. Whoa. How did that happen? Okay, there. Here's what I found out. If I take odds at the level income plus 1 after the salary increase divided by odds at the old level before the salary increase, the ratio is 1.06. Can you remind me what it is? 10615? Is it? 10615. Okay, excellent. Okay. All right. Well, ladies and gentlemen. Well, first of all, my slope was slope was 0.0597, if I remember correct, right? Remember the rule that we discussed? If the slope is positive, then increase in the variable results in increase of odds, right? Okay. So my odds at the higher salary should be more than the odds at the lower salary, right? Is that what's happening here in this ratio? Tell me. I have odds at the higher salary divided by the odds at the lower salary. Which number is higher? In the numerator or in the denominator? The ratio is 1.06. Which number is higher? If I take one number, divide by another number, and the answer is more than 1. Which number was higher? In the numerator, right? So therefore, in DDO, my odds for income plus $1,000 are higher than the odds at the old level of income, right? Agree? Number 1 divided by number 2. If the ratio is higher than 1, then first number was higher. Simple as that, right? Okay, by how much? Let's see. What if my odds ratio, so odds at income plus 1 over odds at income was 1.00? No difference. What would you say? No increase, no decrease, it's the same, right? Okay. What if it was 1.2? Let me give you a hint. Can I say that my number in the numerator is 20% higher than the number in the denominator. Yes, right? Because it basically corresponds to 120%, right? 1.2 is 120%, right? So my odds at the new level of income plus $1,000, they're equal to my old odds plus 20% on the top of that, right? Okay, so what if my odds ratio was 0.75? What would I say? That the odds are going down, right? With income increase, they're going down. By how much? 25%, right? 0.75 means that the number in the numerator is 75% of the number in the denominator. That's what it means, really, right? So the odds went down by 25%, right? So really what I'm using each time is 1.00 as a reference, right? So whatever answer is, I have to subtract 1.00 from that. And in this case, the answer is going to be minus, right? Minus 0.25. Minus means odds decrease by 25%, right? Well, but in my case specifically, let's now get real, right? Let's go to the real example. In my case specifically, the odds ratio was 1.0615. So what's my conclusion? The odds when you get extra $1,000, the odds of you getting a loan from the bank increase by how much? By 6%, 6.15 to be precise, right? Is it difficult? Not really, it shouldn't be, right? So again, I'm using 1.0 as the reference point. If the ratio is above, that means there was an increase in what amount? Well, take the difference and that proportion multiplied by 100 tells you by what percentage I'm going up, right? Same thing if the ratio is less than 1. Subtract 1, the answer is going to be negative, but that will tell you by what percentage your odds are getting down, okay? So with extra $1,000, that's what it says, right? If I'm getting extra $1,000 in income, my odds of getting a loan from the bank increase by 6.15%. The beauty of this situation is in the fact that it doesn't matter what income is my base, right? Always happens, right? We don't specify what was your old income. $70,000, $80,000, doesn't matter. Always happens, okay? If I go from 70 to 71, I'm 6.15%. My odds are going up by 6.15%. If I'm going from 95 to 96, exactly same thing, okay? Make sense? All right. Yes. How far up? Let's do another one, okay? Let's go back and do another one. All right, so now I want to take something that will decrease the odds, okay? So which variable might be a good candidate? Can you tell me? Income has positive slope, so it increases the odds, right? More income. Same thing with family size, right? Positive. Same thing over here. So it looks like we have no choice but do one of the discrete variables, right? One of the categorical ones. Okay, so let's do the online banking, for example, right? Here, okay? Online banking has the slope of minus 0.7605. So, following my same line of thinking, right? I'm not going to repeat the same awful things that I just wrote, all these equations, right? I can just go ahead and straight do the ratio, right? So I'm going to say that odds of online equals yes, right? Divided by odds of online equal no, okay? Because my base is no, right? We discussed that. The base case is no, right? In this case, here, right? Here's what I can do. It's e to the power minus oh god, I forgot what it was, 0.7605, right? 0.7605, and divided by e to the power minus, how much is getting added to the equation for the base case, benchmark. If the online is no, the addition to the equation is what? 0, right? So case yes means online banking yes equals 1, and you get that value added to the equation. Case no means online banking yes equals 0, and therefore there is nothing, right? So minus 0. What's e to the power minus or plus 0 or whatever? 0. Any number in the power of 0 is 1, always, right? So therefore this is 1 really, and this is all I have, e to the power minus 0.7605, okay? All right, well, I think it's already calculated for me, right? Let's see. When I ran this line, x to the power multiple regression, logistic regression coefficient, it's already calculated for me. It's right here. No, hold on. Yeah, it's right here. Online, I can see that. Okay, online banking, 0.4673, right? So therefore, my ratio right here is 0.4673. Okay. So now tell me, ladies and gents, for people who do online banking, are the odds of them getting unsolicited loan from the bank higher or lower than the odds for people who don't do the online banking? The ratio is less than 1, right? 0.46, the last time I checked today in the morning, 0.46 was less than 1, right? So that means that the number in the numerator is higher or lower than the denominator? Lower, right? The ratio is less than 1, that means that you're dividing by a bigger number, right? So therefore, I can, let me erase all that stuff, okay? So therefore, my odds, when I do online banking, online equals yes, are less than the odds if I don't do online equals no, right? Online equals no, okay? Again, by how much? I use as my reference point what? 1.0, right? All I have to do is subtract 0.4673 minus 1. That means odds are not higher, not lower, they're exactly the same, right? And the difference is going to be minus, right? First of all, minus 0.5327, something like this, right? So, odds of getting a loan from the bank for people who do the online banking are 53.27% less than for people who don't do the online banking, right? So once you start doing the online banking, odds of you getting a loan go down by 53.27%. That's what it says, right? Agree? Yay? Cooper, you look confused. Uh-huh. Uh-huh. Yeah. That's income. That's plus 1. But we're talking about categorical variable. In the categorical variables, there is no plus 1, right? Like in the online banking, you have yes and no. That's it, right? In the education, you have BS, MS, doctorate. That's it. There is no plus 1. This is categorical variable, right? You can't add 1. So that's why, really what I'm doing is I'm comparing categories against each other. That's what it is, okay? And in the numerator, there is my base case, which typically comes first alphabetically or numerically, right? So online no is my base case, online yes is what I have variable for, right? So therefore, since this is base case, that corresponds to e to the power 0, because for base case you don't have any addition to the equation, right? But this is my actual case for which I have a dummy variable in the output, right? So therefore, e to the power minus whatever the slope is. Yeah. All right. So, any questions about this one? Now let's do one more case, which is going to be a little bit more complicated, but it's going to be good. Okay. So far we dealt with numerical variable income, right? You know how to interpret. That's plus 1. That's when unit odds ratio comes in. Just now we looked at the binary case, right? Yes, no, 1, 0. Do you do online banking or you don't do online banking? Let's take a look at the case of categorical predictor which has multiple values. And in our case, it's which one? Categorical with more than just two. Education, right? Everything else was yes, no. Do you do online banking? Yes, no. Do you have credit card? Yes, no. Right? But education is three. BS, MS, doctorate. Okay. So, remind me again, from the previous class we discussed that. Let me highlight them. Okay. So, these are my, this is my output for two different levels of education. And why do we have two, by the way? Because it's K minus 1. 3 levels, BS, MS, doctorate, minus 1, that's 2. The base one is what? Bachelors. Why? First alphabetical, right? R or any other software doesn't care. It doesn't make any difference for R what you mean by BS, MS, and doctorate. It takes the first one which comes alphabetically. Simple as that, okay? So, therefore, the addition to the equation on the left side, on the right side, is 0, right? Okay, so if you have doctorate, then it's 3.8182. If you have MS, it's 3.8233. So, based on this output, which level of education has the lowest odds of agreeing to a loan? Bachelor, right? Because it corresponds to plus 0. It's the lowest contribution, right? The next one is doctor, right? It's the next one, right? And the highest one, that corresponds to the highest odds, right? And that would be MS, right? Here is the question. Can I calculate, so true or false, the odds for masters are going, it looks like the odds for masters are going to be teeny tiny, slightly higher than the odds for doctors, right? Because the slope is slightly higher, right? Okay, by how much in terms of the percentage? Here's how I can do it. It's all, these numbers represent the level relative to the bachelor, right? Master versus bachelor, and doctorate versus bachelor, right? But I want to compare doctorate, or which one do I want? Masters versus doctorate, right? It looks like masters are more likely. Odds for them are higher, right? By how much? Okay, let's do this trick, okay? It's not very tricky trick, but still, okay? So, here's what I'm going to do. First, I'm going to calculate the odds ratio for masters versus bachelors, okay? So, odds for MS compared to the odds for BS, okay? It's e to the power, oh gosh, what is that? Hold on. Oh, there is no minus. Okay. E to the power, oh, come on, 3.8233, right? E to the power plus 3.8233 divided by e to the power 0, because BS gives contribution of 0, right? Okay, cool. So it's essentially e to the power plus 3.8233. That's it. Okay? Now I'm going to compute another ratio for doctorates. Same thing, okay? So odds for docs divided by the odds for same thing, BS, okay? Because BS is what I'm comparing it against, right? It's e to the power plus whatever the slope was. So let me get it. For the doctorate, it's 3.8183, right? 3.8183 divided by, again, e to the power 0, right? So BS corresponds to 0 contribution, okay? So 0 is 1 really, so therefore all I have is e to the power plus 3.8183, okay? And now, if I want to compute the ratio, so look at this. This is my dirty trick, okay? If I want to compute odds of MS divided by odds of docs, okay? What do I have to do? You tell me. Here I have my dearly beloved odds for MS. Here I have what I'm looking for in the denominator. What do? I take this expression number 1 and divide it by this expression number 2. Simple as that. Okay? Here's why. Because if I do that, then in the numerator I'm going to have odds for MS relative to the odds of BS, right? And in the denominator I'm going to have odds for docs divided by odds for the same BS, right? And BS cancels out, and all I have really MS in the numerator and docs in the denominator. What I was looking for, right? But at the same time, it's this one, this number, divided by that number, correct? Simple as that, okay? So therefore, all I have to do really, this magnifier makes me jump all over the place. E to the power plus 3.8233 divided by e to the power plus 3.8183. Simple as that. Okay? And they're already calculated, right? I already computed them. Let's go back to the output. Here is my e to the power ms, right? 45.75 something something. And here is my e to the power docs, right? These numbers are already computed. So all I have to do is take the first one in the numerator, right? So I'm going to put a comment here. Okay, calculating odds of ms divided by, let me put it in the bracket, okay, odds of ms divided by odds of docs, right? Doctor, okay? So it's literally this number e to the power slope for the doctorate degree, right? No, MS degree, divided by, I'm going to take the second one, odds for the doctorate, over here, okay? And when I run it, here is my ratio. And we get, like, they were really close, these slopes, right? So therefore, odds are really similar. They're not that different, right? And you can see that from numerical value, right? 0.0503. So you guys tell me now, is that obvious from this ratio that MS degree has higher odds of accepting a loan offer compared to docs? Ratio is 1.005. Slightly, right? Slightly higher, right? By how much in terms of the percentages? The difference between that minus 1.0, right? So the answer is 0.005, which corresponds to what? 5,000 in terms of the percentage. 0.5%. Half percent, right? So if you have MS degree, half of the percent higher, your odds of getting a loan are half of the percent higher than compared to the docs. Right? Practically the same. You're probably right. Statistically, it's not significant, really. Okay, it's the same. Right? It's probably due to the noise that we have this difference. Right? The major difference, of course, is between MS and BS, and also doc and BS. Right? But between them, practically, in statistics, funny story. In statistics, you know how we test hypotheses, right? You formulate null and alternative, you do the p-value, etc., and your conclusion is, at this significance level, there is a statistically significant evidence to support yada, 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 right? But question is, okay, there is a statistical difference, but is there practical difference? For example, one of the problems that I normally do in statistics class when I teach it, on the smoke rooms. You remember the smoke breaks? Did you do that in class? No? Smoke break. So, company, for example, losing some money because employees go out to, smoke a little, right? Those who do smoke. So, they're away from the desk, right? So, company loses productive time, right? So, company decides to install smoke exhaust in certain room so that they can smoke without leaving a building, therefore saving time, right? And we have, of course, like before that, before the smoke room, they have to go out on the street. Company traced, how frequently they're not at their desk, and turns out that on average they're losing 30 minutes a day, okay? And then they check people after they install smoke rooms, and they have like 50 numbers or 100 numbers, right? How many minutes they were away from the desk. And it turns out that the answer is like 26.5 or something like that, okay? As compared to 30. So statistically, if we test the hypothesis, distribution is such that statistically, yes, it's a reduction. But practically, is the reduction? You went from 30 minutes to 26.5 away from the desk. Is that practically significant? No, not really. You're saving 4 minutes of productive time, right? So therefore, there is a difference kind of between statistical significance and practical significance, right? The answer may be statistically significant. But is it really that big of a deal at the end of the day, this difference? Is it huge? So in this case, we probably don't see a huge difference, right? Odds for doctors or masters to get a loan, about the same, right? Okay? How are we doing? Yay? Say meow. There you go. You're not enthusiastic. For some reason. That material puts you to sleep a little? Yeah, this is probably the most difficult thing that we'll do in the class, okay? Okay, so last thing that I wanted to discuss today is, of course, we never address the question of what? Is that a good model or maybe not so good model, right? And that means accuracy, right? Let's do that. It's a little tricky, okay? But we'll do it anyway. So let's see if we can crack this case open. Let's take a look at, first of all, true or false. At the end of the day, I want to classify each of my cases as 1 or as a 0. Yes? Yeah. So therefore, it's a classification problem, right? I'm not predicting really a number, right? I'm predicting, is that a loan taker or not loan taker? 0 or 1? Yes or no? Okay, so it's a classification issue, okay? So, how do we predict the outcomes? We use the function, starts with P, ends with predict. Predict, right, okay. Alright, so let me go ahead and do that, okay? So, but true or false, we also separated data set into training and validation. Therefore, I'm going to see how am I doing on the training set right now, okay? So, therefore, let's calculate training set predictions. Okay? And that's exactly how I'm going to call it. Predictions underscore training underscore set. Okay? Okay, so you told me that I have to use the function predict, right? Pretty much always. It's a universal function, right? Alright, so what's the first thing that I should tell function predict? Predict using which model? Multiple logistic regression, right? First things first, always I have to say what model to use to run prediction. Okay? Next one is what? Data, right? Which data to use? I'm going to pretend it's a new data, but it's not really, right? My new data is going to be the same good old training set that I used to build the model. Or we don't say build, what do we say? Train, right? So therefore, new data is training set. Real not all data, and here is the tricky part, okay? How do I say use logistic regression? Remember what we did for the classification? What did we type? We said type of prediction equals class, right? So here I'm going to say type of the prediction equals, quote unquote, response. Okay? In this case, it will use the formula, underlying formula, and calculate the probability. Okay? So let's go ahead and run this line. And you should see no red color, which means that predictions were okay. Alright, now let's take a look, ladies and gents. Okay? Let's see what we predicted, for crying out loud. So I'm going to say predictions, training set, and just run it, okay? So we'll have what, about 4,000, right? If I remember correctly. Did we split it 5,000 records, right? If I remember. Split 80, 20. That means 4,000 training, 1,000 validation, right? So here is my, here is my bunch of predictions, right? For each record that I have, it actually predicted for me a number, right? What number is that? That's a probability of 1, right? What it predicted for me is probability P that this specific person, that specific customer is going to be a 1. Okay? So, the first one, frankly, it was customer number 1328. Do you have the same? 1328? Yeah. So, 0.001. Is that a 0 or a 1? It's a 0, right? What do we use? 0.5, right? Just like before. 0.5 is our standard cutoff point. Anything above 0.5 is a 1, right? Anything below 0.5 is a 0. So the first customer in the set, number 1328, is a no. Next customer, 0.429, close but still a no, right? Alright. It looks like all of them are no's, right? Oh my god, we're really unlucky. Okay? Alright, so let's scroll and see if we have any yeses. Oh, look at that. 1642, right? The guy number 1642.95. That is a yes. Okay? Then there is 1274 is a yes. 2362 is a yes, right? But the rest of them are no. Okay? So really, here's how I'm going to construct the. What do we need, by the way? Next step. What do we need to do? We need confusion matrix, right? But before with the confusion matrix, let me show you basically how I can do things in R. For example, this is 4,000 observation training set, correct? Okay, so here's what I'm going to do. I'm going to ask my good old friend, function table, to count for me how many yeses I have in the set versus how many no's, okay? Look at that. I'm going to use dirty trick, okay? Never seen it before, so here, I'm going to say, please create a table for me, and in this table, please tell me the predictions training set higher than 0.5. You see that? Higher than 0.5, okay? That's what I'm going to run. Predictions training set more than 0.5, okay? Let's just run this line and see what happens. Bam. Here's my table, and the table says false true. Look at that. Because for each observation it checks the number, is that greater than 0.5? 0.95, yes, true. Next one, 0.001, false. Next one, 0.87, true. Next one, 0.015, false. Right? So for each out of these 4,000 numbers, I'm going to say, is that higher than 0.5 true, or is it higher than 0.5 false? So essentially, when it says true, that is what? Let's see. That are my ones, right? Anything above 0.5, true, that's a 1. That's how I classify them, right? If it's false, if it's not higher than 0.5, then it's too low. It's less than my cutoff 0.5. That's a 0, right? So out of, and by the way, do these numbers add up to 4,000? Yes, Professor, they do. Okay, good. So this is right. Okay, so 4,000 observations. Okay. Okay, so out of them, 301 were predicted. This is predicted results, right? 301 were predicted to be a yes. That's my target group, right? These are the people who will apply, take out the loan when I offer it to them, right? And the majority of them will just say no, right? That's what was expected, really. About 10% or so, 9% really. Okay, these are the people who agree, and the rest of them say, nah, don't need it, don't want it. Okay? All right, so this is how I separate yeses from ones. And look at the trick that I'm going to do for the confusion matrix now, okay? Well, first of all, what do I need for confusion matrix? Is there a library that I may need? Gmodels, right? Assuming that it's installed already, so I'm going to load Gmodels. Bam. Load, okay? Now I'm going to say comment confusion matrix for, what's that? Training set, right? Everything that we've done so far, predictions, that was for training set, right? So I have to compare apples and apples. Training real answers versus training predictions, right? Okay. So I'm going to say cross table, right? Obviously, cross table. But here is the deal. Before that, when we created the confusion matrix, in case of classification tree, I just said predictions, and that was fine. Because my predictions were yes, no, 0, 1, right? Now my predictions actually is a number between 0 and 1, right? But I can distinguish exactly in the same way how I did the table. Greater than 0.5. Okay, so I'm going to say, please cross table for me predictions on training set greater than 0.5 versus the real thing. And how do I get the real thing? The actual answer, yes or no. I go to what set? I go to the training set, right? And in the training set, which one do I get? Which column? Personal loan. That's the real answer, right? We know about each of these people. Did they get the loan or did they not get the loan, right? So that's what I'm doing. Okay, it's a little funky, right? I'm saying here, whatever you predict, the probability separated into more than 0.5 true or more than 0.5 false, right? And plot that against true answers, yes or no. And let's run this one, okay? So I'm gonna make it bigger. Alright, like this. Okay, ladies and gents. So here vertically is my prediction greater than 0.5 false. Yes, sir. Say again? Yeah, there is a minus symbol, isn't it? Right here. Oh, this one? These are just a bunch of numbers that I ran. These are my predicted probabilities, right, of getting a loan, right? Yeah, it's not coming from any data set. It's just 4,000 numbers between 0 and 1. Yeah, so that's why it's not really dollar sign or anything. Okay, so let's discuss that quickly. Okay, predictions training set greater than 0.1 false. That means what? What do I predict? 0 or 1? 0, right? Because greater than 0.5 false. That means less than 0.5. Anything less than 0.5 is a 0, right? So this one is predicted 0, non-papers. And prediction training set greater than 0.5 true. That is my yes, right? Okay, so first of all, it says right here that I predicted 301 yeses. Does that agree to the previous one that we just ran? Counts of yeses versus no's. Yeah, right? Okay. So, ladies and gents, you know how to deal with confusion matrices already, right? You did that for your project. Tell me what's the accuracy. Which numbers do I add to get accuracy? Well, obviously I have to take two positives, which are right here, right? That is a yes, and that is a yes, actually. So 256 plus 2 negatives, right? These are predicted no and actually no. 3568 and divided by 4,000, right? Can I calculate it without doing the add and divide? Yeah, so I have to take that number and add that number, right? So my accuracy is what? 0.956, right? This model has accuracy of 95.6%. Quickly tell me, what is the misclassification rate? It's 1 minus the accuracy, right? 0.044, right? And that can be done by adding that ratio plus that one, right? So 4.4% misclassified, 95.6% are classified correctly. Where in this table is my sensitivity? I'm looking for yeses or nos primarily. Yeses, right? I'm interested who will take a loan. So therefore, I'm looking at the column yes, and where is my sensitivity? It's right here, right? 256 were classified correctly as yeses out of 387, right? So 66.1% is my sensitivity. Added to this number, it should be 100, right? And where is my specificity? It's in this column. So correctly predicted no's out of the total no's, right? And this ratio is right here. 98.8%. Really high specificity. Kind of okay sensitivity, right? 66%, right? Are we cool? Homework for you, ladies and gents, okay? Between today and, when's the next time? Friday. You do the same program for which data set? Validation. Do the predictions on the validation set using the same model, and do the confusion matrix, and see what numbers you will get for accuracy, misclassification, sensitivity, and specificity, okay? And that's what we'll do first thing on Friday, okay? But do it yourself, right? And then come prepared. I will ask you some questions.